This week we talked about graphs of motions and their relationships, kinematic equations, and how to find derivatives and use them to calculate instantaneous values. These are our three graphs of motion, and we use derivatives and kinematic equations to find out how they're related. The derivative gives you the slope of a tangent at any given point. It does this by using infinitely tiny intervals to find instantaneous values, which is why we use limits when finding derivatives. Since the slope is delta y over delta x and velocity is displacement over time, velocity is the derivative of a position-time graph, and because acceleration is change in velocity over time, acceleration is the derivative of a velocity-time graph. For example, let's take x of t equals t squared plus t plus 1, which can also be written mathematically as f of x equals x squared. But since you can't have negative time, we're going to look at quadrant 1 of this graph. So I followed the aforementioned steps to get to my derivative, which is my function for velocity. And I can repeat the same steps to get my function for acceleration. Because the acceleration is constant, the slope of the graph of velocity at any given point will be 2. If we choose points, it will give us the instantaneous position and velocity of each. For example, when t equals 1, the velocity is 3 meters per second, which is the slope of the tangent that will correspond to the point. If we look at the two kinematic equations that correspond to these two graphs, you will find that the derivative of the x1 is the equation for the v1.